And now let us see what asymptotic notations are. They are used for referring runtime performance of an algorithm. That means, as I told you earlier, we can have different algorithms for performing the same task. So when there are different algorithms available, we may have to decide which one is better than the other. So one such calculation can be done over the time consumption. For that we will be using asymptotic notations. These analyses are input bound, meaning that when there is no input to the algorithm, the time complexity is considered as 1 or constant. When there are input, it varies. For its measurement, we use asymptotic notations. These analyses compute operations in mathematical units. For example, the running time of one operation may be computed as a function of n or fn. For another operation, it may be considered as g of n square. That is, here n is varying linearly and here it is varying exponentially. So it can be anything. It can be n cubed or a log n, anything of that sort. The thing to be remembered here is it is a mathematical operation. Asymptotic analysis is a mathematical operation. Here n is the number of inputs. Another thing to be noticed is that when the value of n is very low, different algorithms may result in the same time. നമ്മൾ കണ്ടിട്ടില്ലേ, ഡിസ്റ്റൻസ് കുറയുകയാണെങ്കിൽ നമ്മളിപ്പോൾ നടന്നു പോയാലും എന്തെങ്കിലും മോട്ടോർ വാഹനത്തിൽ പോയാലും എടുക്കുന്ന സമയം ഏകദേശം ഒരുപോലെ വരും. ഡിസ്റ്റൻസ് കുറയുകയാണെങ്കിൽ. ഡിസ്റ്റൻസ് കൂടുമ്പോഴാണ് അതിലുള്ള വ്യത്യാസം വരിക. അപ്പോൾ ഇവിടെ അതുപോലെ തന്നെയാണ്. എന്നിൻ്റെ വാല്യൂ വളരെ കൂടുമ്പോഴാണ് അൽഗോരിതങ്ങൾ തമ്മിലുള്ള വ്യത്യാസങ്ങൾ നമുക്ക് വേർതിരിച്ചറിയാൻ സാധിക്കുക. എന്നിൻ്റെ വാല്യൂ കുറയുകയാണെങ്കിൽ ചിലപ്പോൾ രണ്ടും ഏകദേശം ഒരുപോലത്തെ ടൈമൊക്കെ ആയിരിക്കും തരിക. മൂന്ന് കാറ്റഗറി ആക്കാം നമുക്ക്. അൽഗോരിതം can be of 3 types: best case, average case, worst case. Minimum time required for a program execution is considered as the best case. Maximum time requirement is the worst case, and anything in between these two is considered as average case. Normally we use 3 types of notations for asymptotic analysis. They are the big O notation, omega notation, and theta notation. In the big O notation, we express the upper bound of an algorithm such that, here it is Gn, such that fx falls under this gx for certain value of n. Notice that here we have a k, and after that k, for every value of n, fx will be less than g of x. So when g of x is multiplied by a constant, its plotting will be over this fx for all values of n greater than k. That is the meaning. So this represents the upper bound. Gx represents the upper bound in big O notation. When it comes to the omega notation, Gx represents the lower bound for certain values of n. Okay. When it is in theta notation, we can have two bounds, lower and upper of Gx, and Fx will be in between these Gx. This line will be multiplied by a constant, say C1, this multiplied by a constant C2. So we can have two values C1 and C2, two constants C1 and C2, such that Fx lies between these two bounds, upper and lower bounds. In this way, we can have three types of asymptotic notations. Omega notation expressing upper bound, big O notation expressing upper bound, omega notation representing lower bound, and theta notation representing upper and lower bounds. Some common asymptotic notations are order of 1, which is constant. I have told you that when input is nil, we consider it as order of 1. And logarithmic, order of log n, linear, order of n log n, quadratic, order of n square, cubic, order of n cubed, polynomial, n raised to order of 1, exponential, 2 raised to order of n. Likewise, we can have different asymptotic notations. These things are explained in the coming videos.